Okay, good afternoon. Today we will.
Good
Okay,
afternoon, sir.
so today we will start a new chapter, and that's last chapter. This is chapter number 10. Okay, now this is chapter number 11 as well, and that I'm leaving that on it, and that has like implementation. So abacus or ANSYS. So up to you what you want to use. You have abacus, you have ANSYS. Also, you can download what is called Calculix. Calculix. Okay. So this is it has the same format as Abacus, but this is open source. So the Abacus input file will work here. Yeah. So this is very nice software actually. I have been used and published paper with this. So minimum research level, like high quality work you can do with that. Yeah, so it is freely available. It's freely available, especially it has like a Windows version and Linux version for sure. For OS X also, you have to compile those. So all those, but this for Windows it is very easy. Just install and start working. Linux you have to do the proper the way you do the traditional way, you compile basically and then install. OS X the same way. It does not have the image file. That not just click and you do it. So little bit of as far Linux and OS X is concerned. Otherwise, Windows it is very easy. You can download, you can start working. So at least I suggest you to download this Calculix, and start working it. Yeah, maybe sometime we will give you some demo on this one. Only thing is haven't installed on my system because of this some difficulties I faced. So I will have to get some Windows system and arrange something and then we can do it. But yeah. So, but we can do it. But finally, uh, as I also informed you via your classroom that we have a lab which is I think here on this floor only, right? Next lab. So this is we have a Cad Cam Lab. Although like we don't have much desktops available for working for abacus, but you can go and ask the lab in charge, and you can do those things you can do. Uh, you can also go through the chapter 11 of the textbook, and it has some tutorial. So just follow it. You can do it. So it's right now it is just like following some way, some pre-decided method, and you will get it. Yeah? So you do it yourself. Okay? If you face any problem, let me know. Okay, otherwise it's easy basically. So you have to find some tutorial. You look for some tutorial and search some tutorial. You can do it, or you can follow the chapter 11 and do it. Yeah. Okay. Now regarding chapter 9, we are done, and you know the strong form of the problem that you have to solve, and then you know that in order to solve it, since the problem is difficult, finding analytical solution of 2D elasticity problem is very difficult. So it is so difficult that there is a dedicated uh, course section. And linear elasticity is actually that deals with those kind of, yeah. So it's uh, difficult, and hence using finite element analysis is much easier thing to do, and hence uh, we have been doing all this. Now, one thing before we move to chapter 10 today itself, just want to remind you that, like, if you have three noded triangle element, right? And you remember that n as a function of xy is nothing but linear. Linear, or its equation is planar, right? So it's a linear, meaning that it will be a plane. Uh, Finally, the ux uy will be a linear, meaning that you can interpolate between this and this. If you know you here, and if you know where you are, you can find out exactly what will be the u there, and it will be nearly valid. As you know that equation itself, we have x, like you will have alpha plus x plus gamma y. This kind of this is a equation of a plane, and you, you have three n's, combination of three n's, all the threes are planar only, so you get a plane only, and because of that you get a something, the u, which is a planar, meaning that in x direction is a line, in y direction is a line. That's what it is. Yeah. So that really means that B matrix, which is composed of this and which has this, will be automatically constant. This person should be constant. And you know that if B is constant, this will tell you this epsilon, which depends on, it is a function of B, is also a constant. We have seen that, and if that is constant, then we call this one CST. Okay, if you are in Mumbai, CST is very famous for this right terminus, but not this. Okay, so this is the constant, a straight triangle. Okay. In contrast to what you call it, Elasticity. Okay, so this is LST, linear straight triangle. And linear because you know in this case n will be a function of x square. So this is quadratic, y square, xy, right? Then you will have x, y, and there will be a constant. So this will have all the terms. You can formulate it this as you see, you can say ni xy is equal to alpha 1, alpha I, x square plus beta I, y square, and so on. You can do gamma I, xy, delta I, x, then lambda I, y, plus, let's say, xi. Some xi we have used to use something else. Let's see. In a formula like this, and you know that this is as per the Pascal triangle, and you will get you solve for alpha, beta, and so on, you will exactly get the value of it. And you can solve this, you can actually do it this way. So, good thing about this one is B, which will have del ni, del xj, or del ni, del yj, will be what? Will be linear. The B matrix will have, linear means B matrix a function of xy. Xy means xy, but xy only means meaning that the terms will be something like ax plus by plus c. So, some sort of this kind of you will get. Yeah? B matrix, because B is the derivative of n. So you automatically you get this form. So which is a linear. Yeah. And since this is B is linear, you get a strain is also linear. The strain varies within the element, it varies linearly, or a strain itself is a planar equation, and hence we call it endless. So why we bother? This is about the accuracy. If you want more accuracy, then you have to increase the order of the element, and this is akin to the quadratic elements that you have in 1D. Right? So this is in 2D, but Java element you can use this one. Capture more accurate solution. Yeah. Not necessarily the exact solution, but it will be more accurate. Accuracy by Of course, this formulation you can also do isoparametric way. So in general, you can also have, let us say you have a geometry like this, and you have to capture it. So you can use this kind of element also, where you can exactly capture this, which is the curve. Yeah? Those things also you can do, right? Gravitation. And if you like that, I think during the heat conduction problem also we did it. You transfer is you are going to match it into the eta system. So this one you have x and y, and from your not xi eta but xi1, xi2 lambda system, and then you will exactly do like this. So you will have like this 1 0 0 1 half 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 0 0 half. They are going to map like this one and do all the analysis that you have done earlier. So what kind of analysis? X as a function of xi1, xi2, and which is will be equal to summation of n I xi1, xi2 multiplied by xi I equal to 1 to 6. And similarly, y as a function of xi1, xi2 is equal to summation I equal to j equal to 1 to 6 and j is xi1, xi2. Yeah? What's going on? Okay? So once you have that, and then you do the rest of the analysis that you have done for the 3-noded isoparametric element, same kind of to proceed with that. But this is the one thing you can also have this kind of element. So element can be various types, and accordingly you can go with that. Once you have these things, and then you can formulate all the things automatically in I. All those things, from xi1, xi2, you can formulate, right? So what is the value of? So for example, if you want to formulate this one, so this one is, it's very easy to do actually. So let us say this, you call it number 3, this is number 1, number 2. Yeah? So n1, if you want, then how do you find out? N1 will be this equation and this equation, right? So example, I'm telling, right? So n1 xi1, xi2 is equal to some value alpha, let us say, multiplied by this is equal to xi1 equal to 0. So you have xi1 multiplied by this is xi1 equal to minus equal to half xi1 minus 1. So you get n1 equal to this n equal to like that, and so on. So similarly, you can have for these and these equations. For this one, you have this and this. This is xi3 equal to 0. Xi3 equal to 1 minus xi1 minus xi2. And similarly, multiply them, you get it. Okay. Similarly, if you are here, then this equation and this equation. If you are here, then this equation, this equation. If you are here, this equation, this equation. Okay. So it's easy. And then you proceed. You should know the procedure. That's it. Rest you can do the mathematics. Yeah. Any question, guys? Okay. If there is no question, we will start chapter number 10. Okay, so remember that the objective of this course is not to make you learn some commercial packages, but rather to make you build a commercial package. Remember, okay? So working on that is very easy. You do some tutorial and will do it. Yeah, but actually somebody must have worked and designed those commercial packages, and that start from very small thing. Yeah. So even like a hypermesh, for example, Altair has OptiStruct. There is one module that can optimize the structures. And I heard through my PhD supervisor at University that initial code was written by him. Later on, he was coding. So it starts from academics. You work something on that, and then it is more built upon it. Now, structural optimization is a quite normal in all the packages. If you see all the packages coming with structural optimization, earlier it was debate, it was not there. So ANSYS had little bit, but still sometimes it had bugs and all. But slowly all packages are coming with those. So that's the idea here. You think about something that has not been done, you work on it. So not that some package is there and you use. That's okay. But I think your objective should be also to do something even based on what you hear from. Okay. So now let's start chapter 10. This is the last chapter, and this is about the beam. Analysis of beam. Okay. Now you already have the background. In solid mechanics, you heard about something called Euler or now this beam. So this is the earliest form of the beam, and okay, E or U? Is it E or U? You find out. Okay, now this you start with something like if you recall, I just write it first. If you recall, E, so E like E square. Remember? Not right? Is it like this, right? What? Say again?
Minus
Oh, अच्छा. this uy was equal to m or minus m. That was it. This you are saying, is it? Okay. Okay. So I'm not good at memorizing, but I can get it. So basically m minus m or what we will see. We will really see m or what. This is just to remember what we are going to derive it, so that we also see how they are connected. In solid mechanics, we derive a different way a bit. Here we will derive. It will be different, and this is will be more matured way basically. Yeah. So you can also have that also. There's no problem. Okay. Now, what happens that you have a beam, like this one. And typically this, what you are going to study is how it is deflected up and down, equally to y. And there is an axis in various direction. So basically, if there is a beam, something like this, and then we are assuming that this point can go up and down, right? So that 1 degree of freedom can go up and down, and also it can have a slope. So basically the same beam can, let us say it goes like this. So this is just see. So it will be both. We have to look at the end. What it says that the middle point of the section is just right above it. So meaning that length does not contract, for example. It remains the same. Total length, whatever L here, if we measure midpoint to midpoint, this will be L1. It is not going to contract. This is the assumption in case of a beam. Right? Of course, in that case, we don't have any axial loading at all, right? So here in this, there is no axial loading. All are loading which may be perpendicular to the beam itself. Yeah. Okay. Now, any equation, anything we did brought earlier, we have established based on. First thing is the balance of forces, right? Equation, the elasticity equation, we start with the balance of forces. Elasticity, all problems are like that. Like in heat transfer, you start with the balance of energy, right? How much heat is coming, how much heat is coming. In this case, you have how much are the forces accordingly. Now, what happens is, as I said, the forces will be perpendicular to that. So there could be a distributed load, something like this one, right? And let's call it P, which is a function of x. And because of that load, this is going to deflect. Yeah. And how deflects, this called y, is the displacement in upward direction. Now, we will take a small section of that. So we have a small section. Yeah, and of course, this has some pressure pH, yes, which is upward. And you know that from our solid mechanics that it will have a shear forces. Now, convention there was, typically we wrote downward as a positive shear force, but here we will write this as V, which is upward. Okay, and then And then you have a bending moment, which is sagging direction is positive, so this is positive, and upward, V upward, we are saying positive. Again, this is all your convention, doesn't matter, you can write downward and positive as well, relationship will change. Final equation, you get the same equation. That's not a big deal. But here we are doing so that we match with your textbook as well, so that you are not confused that their equation is coming like this and there it is like just plus and minus difference, but still it should not be confused. If it is like this one, then what happens? You can write here. This is M. What is bending moment? And what do you have here? This is M plus right, dm over dx. Yeah. Similarly, this is V, which is the shear force, and here you get V plus dV over dx. Okay, now balance of forces we have to do. This is a static problem. Yeah, this is not a dynamic problem. Otherwise, you will also take the density into account, and you will get a and you get a wave equation. Okay, right? So here we are not doing that. Force in x direction is equal to 0. In x direction there is no is automatically 0, so we don't write that if y equal to 0. Now from here to here is dx. What do we get? We get here minus v, then plus v dv over dx, right? Plus px multiplied by dx is equal to 0. This is distributed load, right? It's a pressure, right? It's a distributed load per unit, Newton per unit layer, this kind of thing. So, or you get it's gone, and you get what? dv over dx plus px equal to 0, or dv over dx equal to minus right? This is one part of the equation. Second part is you have to also balance the moment, right? This m also has to be 0. Moment about can take any point basically. So let's say from here, from the middle point, yeah. And then what happens? Let's say point m. Let us say. So let's say a equal to 0. This is very small, so we can assume px to be equally distributed, and the moment because of that will be 0. That elements, and then what do we get? We get about this one. We have m plus dm over dx multiplied by dx over 2, right? So this multiplied by dx over 2, and then you have yeah. Huh? Oh, sorry. Yeah. Okay, then minus m, this already moment. So you have minus this one, then you have v. So you have v plus dv over dx multiplied by dx over 2, right? So this is plus, and this is also a plus. Plus you get v dx over 2, right? And that is equal to 0. Yeah.
So it should be V plus del V by del X by del X.
Yes, right. Here minus m plus v plus dv over dx multiplied by dx over 2. Yeah,
Yes.
like that. So we have that, and then we have v dx over is equal to 0, right? It's fine.
Minus V dx.
No, it will be plus only. Anti-clockwise, no? Okay. So or dm over dx, and then we have plus v times dx, and plus we have dv over dx multiplied by half dx square equal to 0. And you know that this is a higher order term, so we will neglect that. So we will get that equal to 0. Okay, so or we get d plus dm over dx, yeah, or d equal to minus, yeah. So we have this equation here, and we put it there. Yeah. So finally we get d square m over dx square is equal to dx. So this is what the FEM equation is. Yeah. So this is the basic. We will also call it a basic strong form. Yeah, most basic strong form. The post balance equation. Now next is bending moment is there, but there is the u. So m as a function of. So that we have to wonder about. Yeah. Okay. Then we have to look at the original problem or original assumptions. When we say Euler-Bernoulli beam equation, it has one assumption that actually it's not correct, but still it simplifies the problem. And what is the assumption? Assumption is that if the beam is like this, let us say, right? So imagine after it's loaded, and if it deflects like this one, then also it says that this angle remains the same. This is 90 degrees. So the way it is here, the same thing, it maintains that. So that really means at the end, it has to maintain 90 degrees. At the end, it has to maintain 90 degrees. All the section will be such a way that section is the cross section is perpendicular to the surface. Yeah. So that's the thing. Yeah. And this all derivation is based on that, and hence Bernoulli. Then later on, you will find out that this does not work for non-linear cases, for high displacement cases. So a small displacement you can do it. Yeah. For if you have the displacement which is larger, then this will not work. This will give you a wrong answer. Or you can do is make a small elements, you solve, then you. Now, anyway, so if that is the case, so let's see how the things are related. So always remember what we did. There are three things. One is the Euclidean equation. Number two is how a stress relates to a strain. This is equilibrium equation number 2, a stress relationship, or you call it, or what do you call it? Constitutive relations. Yeah, this is constitutive relations. Then number 3 is the displacement strain relationship. So U strain relation. So we know sigma and E are related, that it's a linear problem, and you know sigma equal to E times epsilon, because we have a strain which is only one strain in this case. We will look at that also. And then epsilon equal to del U over del X we do in the case of that. But here, how it is related to the displacement? Here displacement is not Ux, displacement is Uy. So we want to find out epsilon, that is strain in terms of Uy, not in terms of Ux. Right? Because this is the one which we need to solve. Okay, now let's look at it. So let's say this is the beam, this is beam, here it is X, here it is Y. Then we call Y, we are talking about that inside the beam. So, like if you have a beam section like this one, then we have Y which is going from some line, yes, some reference line. So that we are talking about. Now let us say this has deflected, and this will go up, and there will be some slope as well, right? So this thing has become this. It's possible, right? So this is the, let us say this is the middle that we are talking about. That, okay, so my diagram is wrong because this has to remain here. Okay, so it will be like, yeah. So same beam which are deflected. So from here, this gone up. We call it Uy. This is a displacement. Yeah. Displacement you measure in terms of the displacement of the what you call it, linear axis, or one reference axis. Yes. This we are measuring at Uy. So let's call it Uy. There is a displacement in x direction as well. Yeah, and you can see that. Let's say there is a point, there is an extreme point. Let's say call this one. This had gone here. So that means if you see, this is the diff. This one is the displacement. Right? So for any point, let us say the point this one, which is like this one, from here to here, we will call it as Ux. Reference point, let's call reference point capital P. This is a point P, and this has moved Ux in x direction, right? Yeah. Although it is related to the slope, right? And what is the slope? Slope is this. This is theta, right? You are with me? This is the slope, and you can see, like if you know the slope, and distance from here to this point is what? From here to here, some point y, right? So here we are talking about some point y. So this is y. This is point y. Then Ux, can you write it as Ux equal to, from here to here you have y. So from here to here you have y. This you have is theta. So this actually here y was the same thing. Theta is very small, by the way. Yeah. So What will be the value of this? This will be y sin theta. Y sin theta. Y upon sin theta. No, it's very small. Very small, no? It's the yeah. We are talking about the component. Yeah, so even if you can also see here, I think you can also draw like this. So we have like this, and we are talking about so distance we want from here to here. So we want here to here, right? So maybe I should have drawn this. So let's draw like this one. So here from here to here we have y, so not this one, and this is so y is from here to here. This is the original y. Yeah. So here to here is the y. So here to here in parallel is y. So this is y. Then this is theta, and then from here to here this is y cos theta. This becomes y sin. Yeah. Anyway, theta is very small, so you can write like if some distance here is theta, component of that will be will be y cos theta here, y sin theta. So we are talking about the component of that, and you get like this. Another thing also you notice that if y is negative, x is positive. Here displacement will be negative. Here displacement will be positive, and our y is positive upward. Yeah. So basically, what we need to say is ux be minus y sin theta. Yeah. Our convention y is positive upward. Yeah. So yx is ux equal to minus y sin theta. Yeah. Fine. Or theta is very small, we can write ux equal to minus y. This is assumption that theta is very small, u is very small. Otherwise, we cannot apply the Euler Bernoulli beam equation. So you have that. Yeah. And what is theta? Theta is equal to. So here, this is uy, and theta will be equal to. This theta will be equal to duy over. This is the slope of the beam itself. So this is duy over dx. Yeah, and hence you put it here, and from these two you get ux is equal to minus y duy over. Right? So what you see here is the displacement. The both displacements ux and uy are related. As the okay. So what is the next? Ux is known. So a strain epsilon x is given by what? Epsilon xx is dux over du. In fact, we have given total derivative assuming they are function of x only, basically. Yeah. So all things are function of x only. There is nothing in function of y. So hence we can write find x is equal to derivative of uf with respect to dx. Yeah, and that will be equal to what? Minus y and then e square u y over x square. There is nothing function of y, and hence epsilon y is equal to, if we write del uy over del x, del y is equal to 0 since uy is not a function of not a direct function of y, because if you see, this is just how much the reference plane has moved. We are talking about that, basically, yeah, and which is a function of x rather than y, because y for us is what? Y is the how much a point is above this line, right? So, and since uy is the how much the mid plane has moved, it has nothing to do with this y, right? And hence it is not a function of that, and hence you get a find y equal to 0, right? So basically in beam you get sin y equal to 0. Yeah. Then what about the sin xy? You write del x over del y plus del y over del x. Yeah, is equal to, now del ux. See here, this equation. Del ux del y, what will you get? You get del uy over del. So you get del over del y, and you are getting minus y del d, let's say like u y over dx plus del uy over dx. Since ux is a function of x only, so the partial is actually the total derivative. So you get the minus duy over dx plus duy over dx, which is equal to 0. This also tells you that there is no shear strain. So you get only the stress in x direction. There is no other stress. Yeah, that's what it tells you. Yeah. These are the problems, and hence this Euler Bernoulli has problems. Hence these are corrected, and there is something called Timoshenko beam, which gives all corrections, and for that this term is not zero. Yeah. Then this assumption is not true that it is at 90 degrees, because you know that if there is a shear, then corner is not 90 degrees. Right? So Timoshenko beam theory actually modifies the original Euler beam theory, and they propose such that the shear strain is there, and hence it is more accurate. Okay, so we have that. Bottom line is that we have only these to talk about, epsilon xx. We take from here epsilon sigma xx will be E epsilon xx, which will be equal to minus Ey and d square uy over dx square. Right? Okay. Now our equation is still, we have to relate somehow, and since sigma xx is given, we can relate somehow to m, and that's our target. Somehow we do that. Okay, and we will find out. But the first thing is, on a section, if sigma x is there, right? This is a sigma x, and this is a beam. We're talking about that somewhere we will have, you know that with y changes, at some there it's 0, then this will be depending on this value, it goes something like this. That's what it's telling you, right? Because y goes positive to negative, and hence in y it is linear. So there is something linear. The sigma is varying linearly. That's what it tells you. And over the whole section, we can sigma xx dA. If we, so let's say this cross section, if you are looking at this, is something like this. Yeah, this is the total area A. So a small area multiplied by sigma xx, and then we integrate over the whole area A. Let's say A naught. That will be equal to what? Should be equal to 0 because there is no axial loading, and hence if you put that, becomes minus e y d square uy over dx square, then dA over the whole area is equal to 0, right? And dA will have what? dA will have from y, and there is something there. That really means dA is a function of y. So what you will get here is, what you get? This has uy, has nothing to do with y, right? If you take a cross section, only thing remains is y direction and this direction. But we are not talking about x direction. So uy is a function of x, but not function of y and something. Meaning that we can, this being constant, we can take that out, so we get e, then d square uy over dx square, and then you have y dA is equal to 0. What is the meaning of that? Y dA equal to 0, that really means that our reference line passes through the centroid of the cross section. Yeah? Or you call it neutral axis, right? Okay, this tells you that y equal to 0 corresponds to centroid. Okay. Yeah. So now next you can also, we can do sigma xx y dA, and that goes from. Why do you want to do it? This is because we want to find out the m. M is equal to, how do you do? So let's say we have sigma here, sigma xx, right? So this is the plane on which sigma will be there, right? You have, and this is a bending moment m. So how do you calculate? We calculate sigma xx multiplied by y dA, right? Over the whole area will be equal to, so sigma x is positive here, and if you apply a bending moment like this, then what happens? If your bending moment is like this one, then you get the deflection will be something like this, and your stress will be negative here. Right? This stress will be negative. So that really means what? If you have bending moment is M is positive, then the stress here is negative, and hence, and y here y is positive, stress is negative, and hence you multiply by minus to make it positive total, right? So hence M equal to minus sigma x y dA, so that M we have applying like this one. The upper part will have compression, means sigma will be negative, but y is positive. You multiply them together, what you get a negative number. But M is positive, and you know that the M is nothing but the force multiplied by the lever distance. Force is sigma xs multiplied by d area multiplied by y is the lever, and in order to make them positive, you have to multiply by minus. Right? That's the deal. So we get M equal to sigma from here. So we have E minus, we have E, then sigma xx. So again minus here and minus here, minus plus, so it cancels out, plus. So you have E, then y square. So from y here and y there, so y square, right? And then you have d square y, dx square. Fine, is equal to d square uy over dx square, and then you have e here, then you have y square dA over the whole area. What is this one? I d square uy over dx square. Yeah, which is equal to m. M equal to ei d square uy over dx square, because this term is nothing but yeah. You got it? Okay. Once we have that, then rest is, remember the original equation we had d square m over dx square equal to px. Originally we have derived. So you put that value here, both together, and what we get? We get ei d4 uy over dx4 is equal to dx. This is the final equation. This is the strong form that we have to solve. So we have ei d or 4 uy over dx4 minus px equal to 0, and subject to, and always there will be boundary conditions, and you have to that for beam there are only two ends, right? This is the gamma 1, gamma 2. At these two ends you have to apply. So there will be some given, right? So which all things are given? uy equal to uy as gamma at some gamma 1. Example, all these are examples, right? Then we will have also given del ui over del x equal to theta at somewhere at gamma 1 and gamma 2, depends. These are an example. And the other places maybe some moments are given, so maybe m is given. So moment, that means this. So possible that uy d square uy over dx square equal to m bar at gamma 2. These are examples, right? And v may also be given, and v was minus ei T3 over Tx cube equal to V. Yeah. Right. So these are the examples where this is nothing but displacements may be given at some points. The bending moment may be given, shear force may be given. So there are the four combination. The order, if you see the order of the differential equation is what? 4. Hence you have 4 boundary conditions. Right? So this is what we have to solve. Okay? So we will see next time how to solve. Any question? Any question, guys? Okay, there is no question. See you guys on Wednesday.